The molecules are always colliding with each other and also collides with the walls of the container. These collisions are perfectly elastic. Here, momentum and kinetic energy is conserved means elastic collision. Momentum means the product of mass and velocity. Kinetic energy means the energy possessed by a body by virtue of its motion is called kinetic energy. Both are conserved in elastic collision, so that the molecules colliding in this collision is perfectly elastic collisions. The number of molecules per unit volume of the gas, the number of molecules per unit volume of a gas remains constant. You're considering one container of certain volume, per unit of volume, the number of molecules should be constant. Now, between two successive collisions, molecules move in a straight line. Between two successive collisions, molecules move in a straight line with uniform velocity. Between two successive collisions, molecules move in a straight line with a uniform velocity. Molecules exert the certain pressure on the walls of the container. Okay, between two successive collisions, molecules move in a straight line with a uniform velocity. Molecules exert the certain pressure on the walls of the container also. The time spent in collision is negligible as compared with the time spent in traveling between successive collisions. Okay, the time spent in collision is negligible. Collision is taken very less time, but it is more in traveling between two successive collisions. The traveling distance between two successive collisions is called mean free path. Okay, mean free path, the average of all these paths is nothing but average mean free path. Okay, ma? Next, transport phenomena. After that, kinetic molecular theory of gases, average kinetic energy of a molecule of a gas. Next class we will discuss. Now we will go for transport phenomena. This is a lengthy question. Later we will discuss. Next we will go for transport phenomena. Most probable speed, root mean square, all we derived in this one. Next, first we'll go for transport phenomena. What is transport phenomena means? It is changing the see here transport phenomena. Is it visible on the screen? Now next topic is postulates of kinetic theory of gases. What is kinetic theory of gases? What we are studying in that means what is the behavior of gas molecules we are discussing, and what are the assumptions we are considering over. Now we'll discuss the topic is transport phenomena. This is also one of the important question in this kinetic theory of gases. In this, what we are discussing, in a steady state of a gas, each transport like momentum, heat energy, and mass would be balanced by an equal and opposite moment in the reverse direction. By be balanced in an equal and opposite moment in the reverse direction, and as a result, there would be no net transport. So once one layer to the molecules are moving forward direction, then one layer to other layer, momentum will be changing. Well, the particles are moving with different velocities. So the product of mass and velocity is called momentum. Then one layer, if the particle moving with more speed, it gains more velocity. More velocity means it having more momentum. Therefore, momentum will transporting from one layer to another layer. At what time it will be reaches? It comes to equilibrium state. Like that, temperature means heat will be transported from one layer to another layer. Like that, mass will be transported. If one is having less mass means one is more means the transport from higher region to lower region. No? Therefore, the momentum, heat energy, and mass would be balanced by an equal and opposite movement in the reverse direction. And as a result, there would be no net transport, and as a result, there would be no net transport. That is called transport phenomena. If the gas is not in a steady state, if the gas is not in a steady state and there are places of concentration of momentum, so if there is not in equilibrium state, not in a steady state, there are places of concentration of momentum or energy. It means heat energy or amount of heat energy or mass in some region of the gas. Hence, the momentum or energy or mass. Hence, the momentum or energy or mass will be transferred, or mass will be transferred from this region to another through molecular collisions, from this region to another with molecular collisions. This phenomenon is known as transport phenomena. This phenomenon is known as transport phenomena. What are the examples for transport phenomena? Viscosity, thermal conduction, and diffusion. Viscosity, thermal conduction, and diffusion. So momentum transport from one layer to another layer, viscosity will get. Heat energy is transferred, means temperature will transport from one layer to another layer, thermal conduction will occur. And mass means density will change from one layer to another layer. Then you are getting the diffusion coefficient and diffusion mass. Like that, three values will change from to get the stable state or steady state, equilibrium state. We get the three types of values, which is viscosity, thermal conduction, and diffusion. Then how much momentum will transport? Then we are getting the coefficient of viscosity. How much temperature it will transport? That we are getting the coefficient of conductivity. And how much mass or density will change from one region to another region? We are getting the diffusion. Is it okay? That is the definition of transport phenomena. Is there any doubt? Now we want to discuss about the viscosity of a gas and what is the coefficient of viscosity of gas. For that, now we will considering viscosity of gas definition. What is viscosity? The components of velocity of molecules may not have same value in all parts of the gas. Okay, all molecules are not moving with same velocities. No more. One molecule is having one velocity, another molecule is also another velocity, different parts of the gas. Therefore, this results in relative motion of the gas layers. These velocities are different in different molecules, means the relative motion of the gas layers with respect to one another will change velocities. Now the layers moving with greater velocity. Now the layers moving with greater velocity transport momentum to the layers of lower velocity. Okay, which is having more velocity means it transport the more velocity. It transport the more momentum to the lower layers of lower velocity. This gives rise to the phenomenon of viscosity. So that momentum will transport in viscosity concept. For this, now you want to calculate the coefficient of viscosity. For that, we can take the derivation part. That also important. In exams, finally, they're asking discuss the concept of transport phenomena. In VSAQ, 5 marks means we write this definition and definitions of all three: viscosity, conduction, and diffusion. If not, if it is essay means we want to derive the all derivation parts, equations also. Any two they are asking, not all. Here 3 is there. Any two they are asking in essay question. That is 15 or 20 marks. Okay.
Okay.
For that, here you are assuming one level diagram. Here the molecules moving along in a plane, xy plane we are considering. Here a gaseous molecule are moving along a horizontal surface. Near to the OX axis, there is no molecule. If you are going upwards, the molecules are moving with a parallel to the direction of X axis. Now assume the gas to be consisting of layers over a horizontal surface OX. Consider a gas in motion along a horizontal surface. Now assume the gas to be consisting of layers over a horizontal surface OX. Okay, ma. Consider a gas moving along a horizontal surface. Here, assuming layers over a horizontal surface OX as shown in figure. First layer is AEF, middle layer is AB, and above layer is CD. Okay, AB, CD, EF layers we are considering, ma. First we are consisting, middle layer is AB, it moving with velocity V. The particles in that layer moving with velocity V. If down layer moving with minus lambda into velocity gradient, dou V by dou Y. Similarly, above gradient is plus. What is the difference between first layer to second layer? Lambda. Similarly, second layer to above layer, A to E also lambda difference, and A to C also lambda difference. Therefore, multiplying with velocity gradient with lambda, path difference. Therefore, above is V plus lambda into dou V by dou Y, and below is V minus lambda into dou V by dou Y from the middle layer AB. Are you following, ma?
Yes, ma'am.
Okay. The velocity of the layer in contact with the wall of the surface is 0. Here, what it is, inside, near the wall of the surface is 0, and the velocity of the layers increase with increase in distance, from the fixed layer. Here, fixed layer velocity gradient is dou V by dou Y. Therefore, now here we are considering a layer AB at a distance y from OX axis. Now we are considering one layer. Number of layers is there. Here we are for the derivation part we are taking 3 layers. First, from the distance y, we are considering one layer AB from the OX axis. Let V be the velocity with which the gas flows in this layer. V be the velocity with which gas flows in this layer. Later, consider 2 layers. What it is? CD and EF. Above and below AB respectively. CD is above the AB, EF is below the AB at a distance lambda from the fixed AB. Okay. Hence, the velocity of the gas in layer, CD is equal to, generally what is velocity? V. Above layer means plus lambda into dou V by dou Y, and below the layer means minus lambda into dou V by dou Y. Okay, ma. The velocity of the gas in the layer CD is V plus lambda into dou V by dou Y. That is velocity grade. Generally, V, ma. Above is lambda into dou V by dou Y. Below is minus lambda into dou V by dou Y. Then CD, EF, how much velocity is there? We can calculate it. Now, the molecules of the gas above AB have a greater velocity. The molecules of the gas above AB have a greater velocity and hence possess a greater momentum because of addition. Greater momentum than those below it. Hence, some of the molecules above AB move downward, while some molecules below AB having lower momentum will be moving upwards. Okay, ma? Above is below and below is above. As there is no mass motion in y direction, only x direction the mass is moving, as there is no mass direction in y. As a result, the number of molecules moving downwards must be equal to the number of molecules moving upwards. Okay. As a result, the number of molecules moving upwards, okay, is more than that of the downwards. Due to this transfer of momentum, takes place. It arises viscosity. Is it clear, ma? AB having lower momentum will be moving upwards as there is no mass motion in y direction. Therefore, as a result, the number of molecules moving downwards must be equal to the number of molecules moving upwards. Due to this transfer, the momentum it takes place. It arises viscosity. Whenever momentum is transferred, it arises the viscosity concept. Now, let small n be the number of molecules. Number of molecules per unit volume of a gas. Small n be the number of molecules per unit volume of a gas. C bar be their average velocity. C bar be their average velocity, and m is the mass of each molecule. Let n be the number of molecules per unit volume of a gas. C bar be their average velocity, and m is the mass of each molecule. We're assuming that now the molecules of a gas move at random in all directions. Here you're considering gas molecules, how much n number of molecules. What is the average velocity of each molecule? C bar. What is the mass of the molecule? M. Now the molecule of a gas move at random in all directions, and 1/3 of the total number of molecules. Molecules can be assumed to move along any of three axes. 1/3 into 1/2 means 1/3 directions, 1/3 into 1/2 x and y plane, no? Then it is 1/3 into 1/2, 1/6. So that considering molecules are n, then n/6. 1/6 into n/6 molecules are moving upward, and equal number of n/6 of molecules moving downward. Is it clear? Means everything is clear, ma. Above layer, how many molecules are transferred? Below layer, how many molecules are transferred from AB region to n/6 molecules moving upward, and n/6 molecules are moving downward. Hence, what it is, it gains the coefficient of viscosity. So this is clear, students. Is it visible on the screen? After continuation of that one, you want to calculate how many number of molecules are moving up and down. The difference of these two gives the coefficient of viscosity. No, for that the number of molecules crossing unit area per second. How many molecules nc bar by 6. N bar how speed you want to calculate means nc bar by 6. Now the total mass crossing unit area per second means mnc bar by 6. Number of molecules means nc bar by 6. Initially n/6, that multiplying with c bar means nc bar by 6. The total mass crossing unit area per second is mnc bar by 6. The momentum carried downward direction. The momentum carried downward direction. The momentum carried downward direction P1 is equal to 1/6 mnc bar into downward. What is the multiplying with the mass and velocity? No, mass value is mnc bar by 6. Velocity is above direction, carried upward downward direction is v plus lambda into dou v by dou y. Upward direction is minus lambda into dou v by dou y. Momentum is mass into velocity. No, mass value is mnc bar by 6. That is multiplying with above and below velocity gradients. V plus lambda into dou v by dou y is P1. The momentum carried upward direction is P2 is equal to 1/6 mn c bar into V minus lambda into dou v by dou y. Okay. Now the net momentum transferred. The net momentum transferred per second is given by P2 minus, so P1 value you know now, P2 value you know now. Now you want to find out the difference between these two values. Now we want to find out the difference of these two values means we are doing above, below equation minus above equation, upper region minus lower region, P2 minus P1. Then P2 minus P1 in both the first write down P2 value, then you can take P1 value. What is P2 value? 1/6 mn c bar into V minus lambda into dou v by dou y minus 1/6 into mn c bar into nu plus lambda into dou v by dou y. Now in both the terms, which value is common? 1 by 6 mn c bar is common. In both the terms, 1 by 6 mn c bar is common. That into nu minus lambda into dou v by dou y minus minus into plus minus only, no? Minus nu minus lambda into dou nu by dou y. In both the terms, plus nu minus nu cancel. F is nothing but change in pressure is change in according to the impulse definition. What it is, ma? Force is equal to impulse is equal to force into time interval. No, large forcing acting in small interval of time means we are getting there change in pressure difference. Therefore, change in pressure difference P2 minus P1. Now we are getting F. P2 minus P1. Now here we are getting pressure force. Therefore, F is equal to 1 by 6 mn c bar 1 by 6 mn c bar into plus or minus nu cancel, then minus lambda dou v by dou y is equal to minus lambda dou v by dou y means that is minus 2 lambda dou v by dou y. Now minus 2 in this 6 cancel means 3 times. Then multiplying both the terms, we are getting minus 1 by 3 mn c bar lambda dou v by dou y. F is equal to minus 1 by 3 mn c bar lambda dou v by dou y, which is equation number 1. Now, but we know that what is the viscous force per unit area is equal to F is equal to minus neta dou v by dou y. Viscous force per unit area can be taken as from the definition of viscosity. F is equal to minus neta into dou v by dou y. Now comparing equation 1 and 2. LHS are same. Now we are comparing equation 1 and 2. What it is, RHS are equating. LHS is same force, viscous force only. Now comparing these two equations, then you are equating RHS. What is the what is that equations? Minus neta dou v by dou y is equal to minus 1 by 3 mn c bar lambda dou v by dou y. In both the terms, minus minus gets cancelled. Dou v by dou y also cancel. Then neta is equal to 1 by 3 mn c bar lambda. Neta is equal to 1 by 3 mn c bar lambda, which is equation number 3. Which is equation number 3. Here in the place of mn, now we are substituting rho. Rho is nothing but density, mass by number of molecules. Then density by mass is equal to density is equal to mass by volume. Here per molecule, how many molecules are there? N. Therefore, instead of mn, now we are substituting rho also. Then equation 3 becomes equation 4. What it is? 1 by 3 rho c bar lambda. Now what is lambda? Mean free path. That value is equal to 1 by root 2 pi n d square. Okay, lambda value is equal to 1 by root 2 pi n d square. Mean free path. Now we are substituting that value in above equation 3. Then what we are getting? Neta is equal to 1 by 3 mn c bar 1 by root 2 pi n d square. Now simplifying this, nn cancel, then what do we have? Neta is equal to mc bar by neta is equal to mc bar by 3 root 2 pi d square. Neta is equal to mc bar by 3 root 2 pi d square, which is equation number 5. Therefore, from equation 4, as the product of rho and c is constant, from equation 4, what it is, as the product of rho and c is constant. Rho is constant, c is constant. Hence, neta is independent of pressure. Neta is independent of pressure, and since c is equal to root t, we have n is directly proportional to root t. N is directly proportional to root t. C is equal to root t means n is directly proportional to c, no? Then automatically coefficient of viscosity is also directly proportional to root t. Otherwise, coefficient of viscosity is directly proportional to the molecular speed of the gas molecule, which is c bar. Therefore, the coefficient of viscosity of a gas, neta, is directly proportional to the square root of the absolute temperature. Is directly proportional to the square root of the absolute temperature of the gas. Okay, ma. This is the viscosity, coefficient of viscosity of the gas molecules from the transport phenomena. Up to this, viscosity is over. Is there any doubt? Next, we'll continue thermal conductivity. If it is clear means we'll go for next transport phenomena is thermal conductivity. How to get thermal conductivity? Due to the temperature difference. Due to the temperature difference, thermal conductivity we will get thermal coefficient of conductivity also we are deriving. Is there any doubt? It is clear means we will start that thermal conductivity. Next one is thermal conductivity. So coefficient of viscosity is mc bar by 3 root 2 pi d square. Otherwise 1 by 3 rho c bar lambda. 3, 4, 5, all three equations are coefficient of viscosity only. So that coefficient of viscosity finally directly proportional to the square root of the absolute temperature. Now we'll go for thermal conductivity. The different parts of the gas may be at different temperatures. The different parts of the gas may be at different temperatures. As a result, the molecules of the gas will transport heat energy, kinetic energy from regions of higher temperature to regions of lower temperature. Okay, ma. The different parts of the gas may be at different temperatures. We are considering one container of gas. Here, different molecule, different parts of the gas may be at different temperatures. As a result, the molecules of the gas will transport. As a result, the molecules of a gas will transport heat energy from regions of higher temperature to regions of lower temperature. This gives rise to the phenomenon of thermal conduction. For that same, how we are deriving in coefficient of viscosity, like that only we are calculating coefficient of thermal conductivity. There we can change from one to another velocity. Here we can change the temperature. For that, first we are considering XY plane here also. The molecules are moving from along X direction, parallel to the along X direction is down region is cold, above region is from the fixed axis AB is hot. Below temperature gradient is dou T by dou V. Before it is dou V by dou V. Now it is along the gradient temperature only. So that middle part is temperature T. Above is T plus lambda. Difference of AB to CD also lambda and AB to EF also lambda. Therefore, we can add the temperature, both the gradients. T plus lambda into dou T by dou Y is above region. T minus lambda into dou T by dou Y below region. Now, consider a gas to be at rest and divided into several layers. A, B, C, D, E, and F. Gas should be considered as rest and divided to the several layers A, B, C, D, and E, F as shown in figure. The different layers are maintained at different temperatures. Hence, there exists a uniform temperature gradient dou T by dou Y in the gas. Consider a layer AB at temperature T. Later consider two layers CD and EF above and below respectively. At a distance lambda for above AB region to CD and AB region to down region is EF, that is also distance lambda. Hence, the temperatures of layer CD, the temperatures of layer CD is T plus lambda into dou T by dou Y, while layer EF is T minus lambda into dou T by dou Y. Similar way, their transport velocity, here transport the temperature. These consisting of conductivity, before one consisting of viscosity. Okay. Don't be confused. The molecules of the gas above are at greater temperature than those molecules of the gas below AB. As a result, the heat transmission takes place. As a result, the heat transmission takes place between the layers due to this thermal conduction takes place. Okay, ma. The molecules of the gas, above AB are at greater temperature than those molecules of the gas below AB. As a result, the heat transmission takes place. As a result, as a result, as a result, the molecules of the gas above AB are at greater temperature than those molecules of the gas below AB. As a result, what you have, transmission takes place between the layers due to this particular thermal conduction takes place. So above region is T plus lambda into dou T by dou Y, and below region is T minus lambda into dou T by dou Y. The molecules of the gas above AB are at greater temperature than those molecules of the gas below AB. As a result, the heat transmission takes place between the layers due to this thermal conduction. As a result, the heat transmission takes place between the layers due to this thermal conduction takes place. Okay, ma. Above is above value, below is below value. Due to that, thermal conduction takes place. Now, let N be the number of molecules per unit volume of the gas. C bar be their average velocity, and M is the mass of each molecule. Therefore, the molecules of a gas move at random in all directions. And 1 by 3 of the total number of molecules can be assumed. To move along any of three axes. Hence, n by 3, 1 by 3 into 2 means 1 by 6 number. Then number of molecules transport is n number. Therefore, n by 6 molecules are moving upward and equal number of n by 6 of molecules moving downward. Same as before only. Now, the number of molecules crossing unit area. Yes, ma'am?
Ma'am, where are we getting this 2 from? 1 by 3 into 1 by 2.
XY plane, no, ma. X plane some molecules and Y plane some molecules. X is 1, Y is 2. Two sides, two different directions, no? XY plane means two-dimensional motion, no, ma. That is, molecules are moving either possible direction is X or Y.
Okay. So that into 1 by 3, which
1
is
by 2.
Random motion in all directions.
Yes, 1 by 3 into 1, two directions only, no? Here, so that all directions multiplying with two directions, 1 by 2.
Okay.
Then it is 1 by 6. Number of molecules in consisting is n. Then it is n by 6 molecules are moving upward and downward direction. How many molecules? N by 6 of molecules are moving upward and downward. Hence, the number of molecules crossing unit area per second is nc bar by. Molecules multiply with the average velocity of the molecules, ma. That is nc bar by 6. How many total mass crossing unit area per second? Okay, number of molecules means multiplied with C bar. Number of mass means multiplied with M also. M and C bar by 6. That is mass. Now multiplying with velocity gradient and above and below. Then we are getting the total energy. M and C, no, according to MC dt. Second law of thermodynamics, it gives no MC dt is the amount of heat energy. Here also you want to calculate heat energy means how much energy transport from above and below. That value you can multiplying with this Mn C bar by 6. Then we are getting the total energy carried downward direction, total energy carried upward direction. First, we are assuming that total energy carried downward direction is Q1, that equal to Mn C bar by 6. Then what is the upward layer temperature, ma? Cv, that Cv is the at constant volume amount of heat supplied to the system, and multiplying with T plus lambda into dou T by dou Y. That is the total energy carried downward direction. That value is equal to Q1. That value is equal to Q1. So that it is clear, ma? Now, what is Q2? That is downward. Mn C bar by 6 into Cv T minus lambda into dou T by dou Y.
Ma'am, what is CV here?
At constant volume, amount of heat supplied to the system. Constant volume, CP, CV, specific heats at constant volume and the constant pressure. No, in interlevel also we have that word. CP, CV. Q is equal to MC dt formula.
Yes,
match.
ma'am.
According to second law of thermodynamics, Q is equal to MC dt. Here M means Mn C bar by 6. We are calculating. The CV means at constant volume specific heat. Temperature means T minus lambda into dou T by dou Y down layer. Okay? You following, ma?
Yes, ma'am.
So the total energy carried upward direction is Q2. Downward direction is Q1. Q1 is Mn C bar by 6 CV T plus lambda into dou T by above means plus. Here below means minus lambda into dou T by dou Y. Now net transfer of heat energy. Net transfer of heat energy is Q is equal to Q1 minus Q2, ma. Net transfer of heat energy Q is equal to Q1 minus Q2. What is Q1? You can substitute. What is Q2? We are substituting. Then in both the terms, which value is common? Mn C bar by 6 is common. Mn C bar by 6 is common, ma. Mn C bar by 6 CV is common. Now T plus lambda dou T by dou Y minus T. Minus into plus, minus only, no? Next minus into minus plus lambda dou T by dou Y. Plus T minus T gets cancelled. Then lambda dou T by dou Y, lambda dou T by dou Y means 2 lambda dou T by dou Y. This 2 in 6, 3 times cancel. Then it becomes 1 by 3 Mn C bar CV lambda dou T by dou Y, which is equation 1. Okay, ma? This is the first expression in total derivation. Finally, what we got? 1 by 3 Mn C bar CV lambda dou T by dou Y. Now, but we know that the quantity of heat that flow per unit area per second is given by how much amount of heat means some constant into rate of change of temperature, no? Generally, we can take as amount of heat transferred Q is equal to K into dou T by dou Y. This is equation number 2. Now comparing equation 1 and 2 marks. According to the principle of definition, Q is equal to K into dou T by dou Y. And equation 1 is Q is equal to LHS are same. Now we are equating RHS. Then K into dou T by dou Y is equal to 1 by 3 Mn C bar CV lambda dou T by dou Y. In both the terms, both the sides dou T by dou Y cancel. Okay. In the place of Mn, we can take as rho. Then K is equal to 1 by 3 Mn C bar CV lambda is third equation. Now instead of Mn, before also we are substituting no rho density. Then K is equal to 1 by 3 rho C bar CV lambda. That is equation 4. Now from equation 3, what is lambda? Lambda also we know that mean free path. That is what is mean free path? 1 by root 2 pi and d square. All these are applications. Equation 3 only final equation. Now we are substituting one time Mn is equal to rho, one time in the place of lambda 1 by root 2 pi and d square we are substituting. Then what it is? Nn cancel. Then K is equal to M C bar CV by 3 root 2 pi d square. 3 root 2 pi d square. Here the coefficient of thermal conductivity. Here the coefficient of thermal conductivity is directly proportional to. Here the coefficient of thermal conductivity is directly proportional to square root of absolute temperature. So what it is, ma, K is directly proportional to C bar, no? C bar is directly proportional to root T. Coefficient of viscosity also directly proportional to square root of absolute temperature, and coefficient of thermal conductivity is also directly proportional to the square root of absolute temperature. Okay, we are calculating coefficient of viscosity in first derivation, viscosity, and in thermal conduction we are calculating the coefficient of thermal conductivity K. That is also directly proportional to the square root of absolute temperature. Okay, two topics over. Any one asking in final exams, they discuss the concept of transport phenomena and derive the coefficient of thermal conductivity or viscosity. Next, last one is diffusion of gases. Same model is there in gases, which will be transport. Momentum will transport, mass will be transport, density will transport from one layer to another layer. Okay, Nana? So diffusion of gases means the diffusion is the process. The diffusion is the process by which the mass gets transferred. The diffusion of gas is the process by which the mass gets transferred inside a gas from a region of greater concentration to a region of lower concentration. The diffusion is the process by which the mass gets transferred inside a gas from a region of greater concentration to a region of lower concentration is diffusion of gases. Here diffusion of gases, which will be transport mass, that also denoted by the letter D. Then D is equal to neta by rho. D is equal to neta by rho is the relation between coefficient of diffusion and coefficient of viscosity. That is also 1 by 3 C bar by lambda. Finally, we are getting 1 by 3 C bar lambda. Okay. Is it clear too? Same. Here, consider certain mass of a gas is moving along positive direction. Same model. Here, dou n by dou v mass. Middle layer AB is nothing but n, and path difference of first layer to second layer is also lambda. And below is what is the gradient? Dou n by dou y, and above is plus dou n by dou y into lambda. Then the concentration of gas molecules is greater above AB, while the concentration is lower below AB. As a result, the mass transmission takes place between the planes. Due to this, diffusion takes place as the molecules are moving in all possible directions, and 1 by 3 of total molecules can be assumed to move along any three axes. Okay. Here, sorry, two axes, X and Y only. Therefore, 1 by 6 molecules are moving upward and equal number of molecules moving downward. Therefore, C is the average velocity. Then what it is, ma? The total number of molecules crossing upward area per second is 1 by 6 C into n plus lambda into dou n by dou y. Similarly, the number of molecules moving downward also. What it is, ma? Crossing upward is upward is 1 by 6 C into n minus lambda into dou n by dou y. Now the difference of these two are calculating. The net number of molecules crossing unit area per second is above value minus below value. Then what it is, 1 by 6 C into, in both the terms, 1 by 6 C bar is common, no? Then we have n plus lambda into dou n by dou y plus minus into plus minus only. Minus n plus minus into minus plus lambda dou n by dou y. Then what it is, ma, plus n minus n gets cancelled. Then 1 by 6 into c into 2 lambda dou n by dou y. Here what it is, ma, 1 by 6 into 2 means 1 by 3 c bar lambda dou n by dou y, which is the net number of molecules crossing unit area per second. But diffusion coefficient is equal to number of molecules crossing unit area. Number of molecules crossing unit area per second. Number of molecules crossing unit area per second divided by concentration gradient. So that what it is, divided by concentration gradient means dou n by dou y. That is 1 by 3 c bar lambda dou n by dou y by dou n by dou y. These two cancel. Then d is equal to 1 by 3 c bar lambda. 1 by 3 c bar lambda. Then d is equal to rho c bar by lambda 3 rho means we can take as n is equal to 1 by 3 rho c bar lambda, no ma. So relation between coefficient of viscosity and diffusion is d is equal to n by rho. Neta is equal to 1 by 3 rho c bar lambda from the first derivation. Now we are substituting in this means neta by rho. Therefore, the coefficient of diffusion is directly proportional to T power 3 by 2. Coefficient of diffusion is directly proportional to not to square root of T, it is T power 3 by 2 and inversely proportional to pressure P. Therefore, D is directly proportional to T power 3 by 2, P power minus 1. Now, relation between all these three we are calculating. First one, according to equation of coefficient of viscosity, neta is equal to 1 by 3 rho c bar lambda. Similarly, according to equation of coefficient of thermal conductivity, K is equal to 1 by 3 rho c bar Cb lambda. Now 1 by 3 rho c lambda Cb bar. Now substituting one another relation, finally we are getting substitute equation 1 in equation 2. Then we are getting K is equal to NCV. Okay, K is equal to NCV. Then K by neta is equal to, no, sorry, neta, that is not N. K is equal to neta Cv. Then K by neta is equal to Cv. Okay, which is the amount of heat supplied at constant, specific heat at constant volume. Cv is equal to coefficient of thermal conductivity by coefficient of viscosity, which is the relation between one and other. This topic is over, ma. Run it out. 3 topics. All these are transport phenomena and relation between one another. K by neta is equal to Cv. Transport phenomena completed. Essay question, 20 marks question. If they're asking essay, 20 marks. If they're asking short answer means 8 marks. Okay? 5 marks, 8 marks, depending upon paper set. Is it clear?
Okay. Yes, ma'am.
Okay. We'll continue next class, ma.
Okay, ma'am.
First lesson, actual distribution, later we will discuss. Next we will start next lesson, second lesson, next class. Okay, ma.